In this video, I'll show you how to use the method of Lagrange multipliers to optimize a function with two constraints. You can use the same algorithm to tackle the problem with either 1 or 2 or 3 or 4 constraints. Let me give you one example. Let's minimize this function. We have two constraints. Let's say x plus y plus 2z must be equal to 9 and 2x plus 3u must be equal to 21. So we have these two constraints. Without any constraints, the minimum value of this function is simply 0. With these two constraints, let's do some calculations. We first need to define this Lagrange function L. So this Lagrange function L is the function to be minimized minus alpha times the first constraint minus beta times the second constraint. So over here, x plus y plus 2z minus 9 must be equal to 0, and 2x plus 3u minus 9 must be equal to 0. So really, L is essentially the same as the function to be minimized, but with these two constraints being included. So this equation holds for any value of alpha and beta. We just then need to determine the values of alpha and beta to minimize the function. To minimize L, we simply say dl over dx is 0, dl over dy is 0, and then we do z and u. We get 4 equations. dl over dx is 0, therefore the first derivative of x squared is 2x, and then we have negative alpha from here, and then we have a negative 2 beta over here in front of x, so right here. What about dl over dy? Same thing. We take the first derivative of this, we get 4y, and then we have negative alpha. Y does not appear here, so it's just 4y minus alpha is 0. We do the same thing for z and u. Again, we get 4 equations. These 4 equations allow us to express x, y, z, and u in terms of alpha and beta. So we have those here. And then we have two constraints, right? If we have two constraints, we have two, again, Lagrange multipliers. They're alpha and beta. So we got 2 equations. From those 2 constraints, we plug in the expressions of x, y, z, and u in terms of alpha and beta into the 2 constraints. Now we have 2 equations. Again, these 2 equations are from the 2 constraints. Alpha and beta are the 2 Lagrange multipliers in front of these 2 constraints. Fortunately, those are just linear equations, really easy to solve. So this one is simplified to this. This one is simplified to this. Now I want to cancel this alpha, so I multiplied this equation by 5/4. I got this, and then I take the difference between these 2 equations. I removed alpha, and I got this beta has to be 4. When beta is 4, we plug in this beta equals 4 here. I got alpha equals 4. It just happens alpha equals beta equals 4. This is coincidence. All right? And then once we know the values of alpha and beta that minimize the function value, we can actually obtain the values for x, y, z, and u correspondingly, because we have the expressions of x, y, z, and u in terms of alpha and beta. And then let's just verify the constraints. X plus y plus 2z is this, equals 9, good. 2x plus 3u equals 21, that's good. And now let's look at the function here to be minimized. We plug in the values of x equals 6, y equals 1, z equals 1, u equals 3. We plug them in. The result is 6, 0. So the minimum value of this function is 60, given these 2 constraints. All right, so in summary, if you want to minimize or maximize a function of multiple variables with multiple constraints, let's say we have 2 constraints, g equals 0, h equals 0. Then you just need to set this Lagrangian L equals this function f minus alpha times g minus beta times h. Alpha and beta are Lagrange multipliers. G and h are the constraints in the form of an equation being 0. Again, this is to ensure that L is f, regardless the values of alpha and beta. L is always f. Therefore, we can just minimize L to minimize f. So now we minimize L by taking its derivative with respect to all those variables. And then we get a bunch of equations. These are linear equations. And then we can express, well, okay, they don't have to be linear equations, but sometimes it's just easier with linear equations. So we got n variables, and then we have n equations. With these n equations, we can express these n variables in terms of alpha and beta. And then remember, we have two constraints, right? G equals 0, h equals 0. Now we just plug in the x1, x2, x3 in terms of alpha and beta into the two constraints. And then what do we have? We have two constraints, two equations. And now these two equations contain only two variables. One is alpha, one is beta. If you have two equations that contain two variables, on paper, we can solve these two equations. We can get the values of alpha and beta. And then we plug in the values of alpha and beta in here. We get the values of x1, x2, x3, etc. to minimize this L. And if we can minimize L, that means we minimize this f with these two constraints, g equals 0 and h equals 0. Again, this is because L equals f regardless of the values of alpha and beta. And we did this to ensure that L is either minimized or maximized. All right? This method of Lagrange multipliers is very useful in physical chemistry because we can use this method to prove that the Boltzmann distribution is associated with the maximum number of microstates under the constant Ne constraints. So that means while we have a constant number of particles, we have a constant energy, and this Boltzmann distribution gives us the maximum number of microstates. And this allows us to estimate very accurately the entropy of the system with a constant number of particles and a constant total energy.